Hello, everyone. This is the last lecture of the second part of this course, dedicated to the phenomena in semiconductors. Um, in this lecture, I will tell you how to use what we have learned about conductivity due to electrons and holes to measure the recombination time. Um, then I will describe the phenomenon of diffusion and will introduce Einstein's relation, so not so many topics, and I think this lecture will be fairly short, but we'll see how it goes. So let's begin with the recombination time measurements. So we have discussed recombination time, but how is it measured? The standard procedure is to measure the so-called photoconductivity, and here is the description as experimental setup. So somewhere here you have a semiconducting sample um, and a source of light, and that source of light produces light which is modulated in time. So the intensity of light goes up and down. So maybe it is a laser, and in front of the laser there is a wheel which has holes in it. The wheel is rotating. As the wheel is rotating, the holes uh, the wheel will be either blocking the light incident on the semiconductor or will let that light through those holes because the holes are rotating together with the wheel. So that's the simplest way to produce this light pulses incident on the semiconductor. When the light in a particular pulse enters the semiconductor, it generates electron-hole pairs. So the concentration of electron-hole pairs increases in time in proportion to 1 minus exponential to the power minus time t divided by tau, the recombination time. And so as the concentration of electron-hole pairs increases, so does the conductivity of the sample. And so does the current. So the sample is kept under a small voltage, and there is an ammeter which measures the current. So the current will also be increasing. Now, during the off phase, light is no longer generating those excess electron-hole pairs. Hence, the concentration of excess charge carriers delta n decreases as exponential to the power minus t divided by tau, and so does the conductivity of the sample. So in both these expressions, we have derived these formulas in the previous lecture. So delta n naught in the first expression, when the light is on, that is, this is the on phase, the concentration of the excess charge carriers evolves in time according to this kinetic equation, and we are applying the recombination time approximation. So we have the time derivative of the excess carrier concentration is the non-thermal generation rate due to light minus the net recombination rate, which is characterized by the recombination time tau. And the net recombination rate is delta n divided by tau. And the solution of this equation has been derived in the previous lecture. Not in the previous lecture, in a couple of lectures before, when we were talking about the recombination generation processes. So at the time t, we are measuring time t from the beginning of the on phase. So at the time t, the excess carrier concentration is the concentration in the beginning of the on phase, delta n of 0, times exponential to the power negative t over tau, plus the non-thermal, the light generation rate, times recombination time tau, times 1 minus exponential minus t over tau. And this function goes like this. And in an off phase, the charge carrier dynamics is described by the same differential equation, but without this non-thermal generation rate. So it is d delta n by dt is negative delta n over tau in the off phase, and the solution of this equation is written here. It is an exponentially decaying function where delta n of 0 is now the charge excess carrier concentration in the beginning of a given off phase. So delta n of 0 exponential minus t over tau. And so by measuring the time-dependent current for on and off phases, you should be able to determine this recombination time tau. So that's the idea of these experiments. So actually you can measure the photoconductivity, that is the conductivity delta sigma, which is due to light. The net conductivity is given by the general formula, which consists of the electron and hole contributions. So E elementary charge times the concentration of electrons multiplied with the electron mobility plus concentration of holes multiplied with hole mobility, close the brackets. And the electron and hole concentrations are the sums of their equilibrium values, N naught and P naught respectively, plus excess concentration of charge carriers, delta N. So you can split the total conductivity into the equilibrium value, which is given here with the charge carrier concentrations set to their equilibrium values, N naught and P naught, plus the photoconductivity delta sigma, in which delta N, the excess carrier concentration, which is common for electrons and holes, can be taken outside the brackets. And now in the, let's say, if you're looking at the off phase, then since delta n of t decreases exponentially, so does the photoconductivity. And now you can measure the recombination time by dividing both sides of the photoconductivity by the initial value in the beginning of a particular off phase, take a natural logarithm and dividing the time t by the natural logarithm of delta sigma of t over delta sigma in the beginning of an off phase. So that's your recombination time. Okay, so this is a fairly simple but very efficient technique. Simple doesn't mean bad. Simple usually means great. The simpler the better. Now let us move on to the next topic of this lecture, diffusion. You have witnessed diffusion in everyday life. Even somebody opens perfume in one corner of the room, and sooner or later, somebody in the other corner of the room can feel this nice smell. And there are other ways to witness diffusion, which I will not be discussing here. Use your fantasy. Now, what happens is this. If you have a region in space where you have more particles of a certain kind, for example, atoms of the perfume, then those atoms are more likely, statistically more likely, to leave that region than to go back to that region. Atoms find themselves in the state of perpetual thermal motion, random chaotic motion. And in principle, for each individual atom, in the symmetric situation, when there are no fields, no forces acting on the atoms are as likely to go left as to go right. There is no preferred direction. But if you have more atoms concentrated in one region of space, then statistically atoms are more likely to leave that region than to enter that region. And this is called diffusion. Now you can apply the same description to think about electrons and holes in a semiconductor. But let's just, for now, let us think about particles in general. This can be electrons or holes or atoms or molecules of some substance. So the diffusion flux density can be described mathematically using what is known in physics and in mathematical physics, the Fick's law of diffusion. It says that the diffusive particle current density or the flux density is proportional to the degree, to a parameter that measures the non-uniformity of particle distribution in space. And the degree of this non-uniformity is simply the gradient of the particle concentration. In 3 dimensions, the gradient is a vector whose components, 3 components, are the derivatives, partial derivatives of the particle concentration with respect to x, y, and z coordinates. But here, for the sake of simplicity, let us focus on the one-dimensional case, and the gradient becomes just the derivative of the concentration with respect to a particular spatial coordinate x. Then the particle current density, its direction is against the gradient. So it is directed from the regions where the concentration is large to the regions where the concentration is small. And it is simply proportional to the gradient. The fact that the particle current density is directed against the gradient is reflected by this minus sign in the expression for the particle flux density. So if the concentration increases in the x direction, let's say dN by dx is positive, concentration increases in the x direction, then the particle flux will be in the negative x direction, hence this minus sign. The proportionality constant, capital D, is called the diffusion coefficient. In semiconductors, you need 2 diffusion coefficients, one for electrons and one for holes. They both enter the expressions for the flux of electrons due to diffusion and for the diffusive flux of holes. The diffusion coefficients are properties of the material. They depend on the parameters such as temperature, doping concentration, and they have the typical values in the range of centimeters squared per second. Now, why is the diffusion coefficient measured in centimeters squared per second? Let's look at this expression for the diffusive flux density. Again, the flux density is measured, let me remind you, flux density is the average number of particles that goes per unit time through a unit surface area. And that surface area must be oriented perpendicular to the average transfer, direction of the average particle transfer. So per unit time means that the flux density has inverse seconds in its units. Per unit surface area means that it has inverse square centimeters in its units. So the flux density is measured in 1 over centimeter squared per second. Centimeters to the -2, second to the -1. The gradient of the concentration, dN by dx, is measured in concentration is measured in centimeters to the -3. And then you have x in the denominator or dx in the denominator. So altogether, dN by dx is measured in centimeters to the -4. Hence, the diffusion coefficient is measured in centimeters squared per second. And like I said, in semiconductors, it has the typical value in the centimeter squared per second range, from 1 to about 100 centimeters squared per second. Now, I come to an interesting result, a very non-trivial, simple yet non-trivial result known as Einstein relation. So here is the physics. There are 2 seemingly unrelated phenomena, drift and diffusion. Drift emerges when you apply an electric field and particles start moving in response to the electric field, but they are not accelerated. They move at an average, at a fixed average velocity known as the drift velocity. And drift velocity is the product of charge carrier mobility, mu, times the electric field. The drift transport is directed along the electric field for positive holes and against the electric field for negative electrons. And then you have another phenomenon, diffusion, which I have just described. The diffusive current density is negative diffusion coefficient times the gradient of the particle concentration, or in one-dimensional case, it is the derivative of the particle concentration with respect to the spatial coordinate x. These two phenomena seem to be unrelated, independent of each other, and yet there is a relation between these parameters that characterize the two phenomena, the diffusion coefficient and the mobility. It is simply that the diffusion coefficient is the product of mobility and the thermal voltage, where the thermal voltage is the ratio of the thermal energy kT to the elementary charge E. This relation is known as Einstein relation. And its importance is that, well, you can measure the mobility of the particle. Mobility is can be inferred from the conductivity quite easily, because conductivity is elementary charge times mobility times the concentration of the majority carriers, assuming that the minority carriers contribute very, very little to the conductivity. So you can measure the mobility quite easily, but the diffusion coefficient is not so easy to measure. Einstein's relation allows you to immediately find the diffusion coefficient by simply multiplying mobility with the thermal voltage. Now let us try and understand why this relation holds. At the most fundamental level, the same thing happens to the charge carriers when they drift in the electric field or when they diffuse. They collide with the crystal lattice. So when they drift in the presence of the electric field, the collisions with the crystal lattice, more precisely with the vibrations of the crystal lattice and also with the defects and impurities present in the crystal lattice, those collisions, every time a particle collides with the crystal lattice, its regular velocity obtained from the electric field is reset to zero. Then the particle gets accelerated again and collides again, and the velocity, the energy that it got from the electric field is dissipated into the lattice. So the collisions of the charge carriers with the crystal lattice are responsible for the charge carriers drifting at a fixed drift velocity. Now, as for diffusion, it is the collisions which are responsible for the Brownian motion, for this random motion of the charge carriers due to diffusion. So again, without the collisions, the charge carriers would just go according to the well-known mechanical principle. They would go on a straight line at a fixed velocity, right? But in the collisions, they have to change randomly. Their velocity constantly has to change in time. And so the particle's motion becomes random, irregular. So the same physical mechanism which is responsible for diffusion is also responsible for drift of charge carriers in semiconductors. All right. Now I am going to derive Einstein's relation based on this consideration. Suppose you have some non-uniform distribution of the electric potential. Now, this curve is arbitrary, but suppose there is some non-uniform distribution of charge carriers. Now, this non-uniform distribution of charge carriers is due to a non-uniform distribution of the electric potential. You can produce this non-uniform distribution of the electric potential, for example, by doping the semiconductor non-uniformly with donors or acceptors. For example, if you dope non-uniformly with donors, so there is a region in space where you have a lot of donors. Those donors turn into positive ions, and they give away electrons to the crystal lattice, and they turn into positive ions. So you have a region where you have excess of positive ions. And those positive ions create an electric field, which is directed outward, and that electric field tries to pull the electrons into that region. So you have a non-uniform electric potential in the material. So this potential, let's focus on the one-dimensional case. This potential is denoted as phi of x. X is the spatial coordinate. And the energy of a charge carrier, an electron or a hole, is given by the product of the electric potential times the charge of Q of the charge carrier, where the charge Q is either plus elementary charge if the particle is a hole, or negative elementary charge if the particle is an electron. Now, particle concentration, let's say at some far away from this region, the electric potential has the value 0. So, and the particle concentration C, whatever those particles are, electrons or holes, has the value C naught, far away from that region where the electric potential is non-uniform. So we can apply Boltzmann's statistics to relate the concentration of charge carriers, be it electrons or holes, at a point x to the concentration C naught far away from the region where the electric potential is non-uniform and where the electric potential actually has the value 0. Namely, the concentration at the position x is the concentration C naught times exponential to the power negative energy of the charge carrier, that is negative Q times phi, divided by the thermal energy kT. This is simply the Boltzmann's factor, which gives you the probability to find, this exponential gives you the probability to find a particle at the position x where the potential has the value phi of x. And of course, C of x, C is the concentration, which can be either electron concentration or hole concentration. But we have been using different letters for electrons and holes, so I have kind of unified the notation to include both. All right, so so let's say you have a region where the energy of the particle, the product of the charge, particle charge times the electric potential, is minimal. And according to this Boltzmann's formula, the concentration of charge carriers in the region where the energy is minimal will be the largest. So you have a lot of particles in this region, like that is near the bottom of the near the energy minimum. If you have non-uniform particle distribution in space, those particles will tend to diffuse out of that region. So there will be a diffusive current out of this region, out of this minimum of energy. But on the other hand, the non-uniform electric potential produces an electric field, negative derivative of the electric potential with respect to the coordinate x, and that electric field tends to pull the charge carriers back into this minimum. So the electric field, the presence of this electric field results in an onset of the drift current density, and in thermal equilibrium, the two current densities are not zero, but they must perfectly balance each other. So their sum is zero, so that the net particle current density or particle flux is zero in thermal equilibrium. Drift current plus diffusion current is zero. Okay, now let's think about the drift current. Drift current is given by the product of the charge carrier mobility, mu, be it electrons or holes, times the electric field. The product of the mobility times the electric field is the drift velocity. When you multiply the velocity, drift velocity, by the carrier concentration C, you get the current density. And in order to take into account that positively charged particles drift in the direction along the electric field and negatively charged particles, electrons, drift against the electric field, I multiply the magnitude of the current density with the sign of the charge of my particles. So if Q is positive, then sign of Q is +1, and drift current density is the product of concentration of those particles. Let's say these are holes if Q is positive. Hole concentration times the drift velocity, which is mobility times the electric field. If my particles are electrons, Q is negative, sign of Q is -1, and J drift, the drift current density, is negative concentration of electrons times mobility of the electrons times the electric field. So this is the drift current. As for the diffusion current, it is the negative diffusion coefficient of electrons or holes times the spatial derivative of the concentration of my charge carriers, dc by dx. Now, the concentration of charge carriers is given by this Boltzmann's formula. It is proportional to exponential to the negative q phi of x over kt. So I take the derivative, and the derivative of the exponential to the negative q times phi over kt. It should be negative. Okay, fix the sign. Okay. So the derivative of exponential negative q phi over kt with respect to x is negative q over kt d phi by dx. Okay, so this times this exponential. So this, and the negative derivative of the electric potential with respect to x is just the electric field E of x. And also we recognize that C naught times the exponential is just C of x. So then we can write down the diffusion current from here, negative d C of x q over kt E of x. So negative d is there. C of x q over kt E of x is dc by dx. And we observe that the charge of the particle q it is either positive or negative elementary charge. So q is sine of q times the elementary charge. So instead of q, I write sine of q times elementary charge here. All right, so what remains is to add up the drift and the diffusion currents. Then, of course, so that is this line plus this line, add up to 0. This is the drift current here, plus the diffusion current, they add up to 0. So sine of q cancel out, c of x cancel out, and what remains is the diffusion coefficient in the diffusion current multiplied with E over kt must be equal the mobility. So the diffusion coefficient is mobility times the ratio of thermal energy divided by the elementary charge, or it is the product, diffusion coefficient is the product of mobility of the charge carrier mobility, electrons or holes, times the thermal voltage. And this completes the proof of Einstein's relation. In conclusion, I want to say that Einstein's relation relies on classical statistics because we have used Boltzmann's formula. Boltzmann's formula here for the non-uniform carrier concentration. In the degenerate case, that is when the Fermi energy is close to one of the bands, to the edge of the valence band or the conduction band, Einstein's relation breaks down because it is not a law of nature. It is an approximate formula, again, used when the classical physics is valid. In the more general case, you need to apply Fermi-Dirac statistics rather than Boltzmann statistics. So this was the last lecture from part 2 of this course, and in the next lecture we will start discussing some semiconductor devices. Thank you all very much for your kind attention. Goodbye.